Welcome. So, in preparation to the study of subRiemannian manifolds and more generally Carnot-Karateodori spaces, I will now present how a smoothly varying norm on a manifold induces a distance function. So the Finsler structure will define a length structure. The length structure will define a distance function, and the distance function induces a length structure. At the end, we shall clarify that the length induced by this distance function coincides with the initial Finsler length structure. To define a metric structure on a Finsler manifold, we first begin with the characterization of the curves that we want to use to define the length. So these are the absolutely continuous curves. So suppose we have so this does not depend on the Finsler structure, it's about the manifold as a differentiable manifold. So let's say we have a curve on a manifold. We're not assuming that the curve is smooth. We say that it's absolutely continuous, AC, if there exists some coordinate or local parameterization, so local parameterization, for which so since curves are image of intervals, one can actually find a parameterization that covers the whole image of the curve. So this is, AB. And there exists a function L1 B valued into Rn. So this is the in other words, this means it's integrable with respect to the bag measure. With the property that if I consider gamma and then I post-compose with the inverse of phi of C, so I get then, so here didn't write the domain of psi, so like this. So from U to M. So now if I take the inverse, I go to Rn. So now this has become a function from AB to Rn. So I can say this function can be expressed as the initial value, which is A, plus the integral from A to T of this function. We're thinking of this is the derivative, okay? So G, so this is the definition of absolutely continuous. And moreover, G is unique almost everywhere, as a function L1, and is called derivative of gamma and is denoted as gamma dot. Okay, so now that we have the curve that we want to, we can make sense of the derivative, we can define the length of a curve. So the length of a curve with respect to a Finsler structure. Okay, so I start with Finsler manifold. And if I have a curve that is absolutely continuous, then I define the length with respect to this structure of gamma as the integral over I of the norm of gamma dot. Okay. First, one should pay attention. I mean, really, this vector is a tangent vector of the manifold. It really does not depend when you have this G and then you put it back via psi to the manifold M. Really, this is independent on the choice of the local parameterization. Right? Actually, yeah. So maybe if this is a problem, one can just see this notion is something. This G is just defined locally, so one can see just in coordinates, then you have this property here. Okay, so now we have this tangent vector. We can take the norm. This is the norm, of course, at the point gamma t, and make sure take the integral. I take the integral of this, okay, of these vectors. Now, let's notice that the fact that gamma is absolutely continuous. So, okay, first of all, is that we have the derivative existent, and also that we have this it's an integrable function. So the length with respect to this Finsler structure is really a finite value. Okay. Then one define the distance with respect to a Finsler structure. What do you do? So the distance between P and Q, this is the infimum of all possible length with respect to the norm of gamma. Okay, I'm writing shortly that this is this. This is another way. I abbreviate length which is L, such that, so what is gamma? So gamma is an AC curve, absolutely continuous, from P to Q. Okay, so this is the definition of the Finsler length. So the length induced by Finsler structures. So some facts that we will discuss. Okay, so first of all, okay, really this distance function defines a distance function. Defines a distance function. Symmetries are quite obvious, and it's positive, and triangle inequality as well, because I can join two absolutely continuous curves and it stays. The joining is absolutely continuous. What is maybe less evident is the fact that two different points really have strictly positive distance. But this is not really a difficult task, because one can really observe that in local coordinate, this distance is locally by Lipschitz equivalent to Euclidean distance. We'll go back to this point. And what I'll tell you, but then I will prove it, but just not to get confused, that at this point we have two distances. We have the distance that we start with, so this distance, we have now that we have the distance, we have a length induced by this distance. So now we get a length that a priori might be different from the previous one. So let me clarify this fact. So if you take the length associated to the Finsler distance, then this is exactly the length defined by the length structure. And it is also true that a curve is AC if and only if then the length with respect to this distance function is fine. Okay, we'll go back to this. Let's see the most basic example of Finsler manifold. Okay? This is the example of a normed vector space. Okay, so let's suppose that we have V with the norm. So V is a vector space. I can think of Rn for some n, finite dimensional vector space, and then let's consider a norm on V. Let's try not to think of the Euclidean, some Euclidean product. Okay, not an inner product, just a norm. Okay? And then one can define the distance between 2 points to be just the norm of the difference vector. Okay, this a priori could be different from the distance we defined before. Right? The distance that we defined before, and we ask if this is the same. So is this equal to what we defined the distance associated to this Finsler structure, right? So this is a manifold. This is actually a constant norm, so it's not really varying from tangent to tangent. So all the tangents spaces are identified with a vector space. On all of them, we put the same norm. So what was this last distance? This was given as the infimum of the length, of course, and the length is done as by integrating the tangent vector. Okay? This when gamma was an absolutely continuous curve, and is from P to Q. So we are asking, is this the same distance? Okay, so this is the derivative of the curve, which exists because the curve is absolutely continuous. Okay, so let's see why these two distances, yes, they are actually the same distance, but why? Okay, so let's start taking one of these absolutely continuous curves. Okay? So take gamma from an interval, say AB to V, absolutely continuous from P to Q. Now, up to reparameterization, we may assume that gamma is Lipschitz. Now, Lipschitz, respect to what? Okay, either with respect to the norm, or equivalently with respect to some scalar product or some Euclidean distance. And this is because all the vector spaces of the same dimension, they're the same, can be identified, and all the norms are by Lipschitz equivalent. Okay. Okay. So considering here the Euclidean distance, we can say that gamma has finite Euclidean distance and therefore can be parametrized by arc length, and therefore being one Lipschitz. Okay. But then, by Rademacher theorem, the curve gamma is differentiable almost everywhere. Actually, we already did this discussion when we wrote this integral. So this integral makes sense because this this derivative exists almost everywhere, right? Okay. But okay, reparametrizing, we can really think that this is bounded by the Lipschitz constant. Okay. But now the curve is differentiable. So now let gamma prime of t be the derivative where it exists at the point t. Okay, so what do we mean? We mean the derivative is at increment h is equal to gamma t plus gamma prime t plus times h plus a little o of t, a little o of h. Okay, so let's continue. So now let's calculate the metric derivative. Let's calculate the metric derivative. So I will denote the metric derivative of gamma dot t. So this was, by definition, was the limit of the distance. Now the distance is the norm. So the distance between gamma t plus h to gamma t divided by the norm of h. The norm of h, the absolute value of h, right? So now this is the limit for h going to 0. This is equal to, so let's use the fact that the curve is differentiable at t. So instead of gamma t plus h, we put gamma t, which gives this. So this difference is equal to gamma prime t times h plus little o of h. Okay, so this is divided by h, norm of h. You see? Yes, okay. Very good. And now this gets simplified, and this goes to 0. Yes, and therefore, as a limit, we have gamma prime at t. So what we proved is that the metric derivative, as the symbol was just like trying to let us think, is indeed the norm of the tangent vector. Okay, now that we know the metric derivative, we can recalculate the length of the curve. So by the theorem we proved previous video, by the previous 2 videos probably, of length as integral of metric derivative, we have that the length with respect to the distance we are considering, here we're considering the distance given by the norm, is equal to the integral of the metric derivative. But now, as we saw, the metric derivative is really the norm of the derivative, and this was by definition the integral, so there was the length induced by the Finsler structure of gamma. So what we have understood is the two length structures coincide. The one given by the distance d, and the one given by the structure, by the Finsler structure. Okay, let's see what this tells us about the distances. So, regarding the two distances, so it's d and d given by the Finsler structure. So d of the distance between 2 points, so this was by definition p minus q. Okay, so now if we take any curve for all gamma curve from P to Q, so the distance, the length of the distance is always greater than the distance between the endpoints. Why? Because, you know, you can take the point PQ as partition of the times of partition. I mean, the initial time and the end time for gamma as partition, right? So this was the subRiemannian. So this is always true in any magic space. Okay, but now we saw that this is the same length of the Finsler structure. Good. So now infimizing, we get that the distance t is less or equal than the distance induced by the Finsler structure. Okay. But on the other hand, we have a distance for which this is an inequality. It's really the straight line between P and Q. So note that the curve, so you can write it as a convex interpolation between P and Q. This gives equality. Gives equality in here and therefore in here, because this was exactly the infinity. Therefore, the distance given by the norm, by the norm of the difference, is equal to the Finsler distance. This was for a vector space induced equipped with a norm. However, now you can see that this proof that I gave really can be generalized to general Finsler manifolds, and this is the proposition. So suppose you have a manifold I mean differentiable manifold. Then suppose we have a continuously varying norm, then norm, then we fix a curve gamma, to M, it's a curve. Now, first of all, it's okay. The fact that A is absolutely continuous, then it implies that up to rescaling, gamma is Lipschitz and differentiable almost everywhere. Okay. To the metric derivative is really equal to the norm of the derivative. And 3, this gives that the length given by the Finsler structure is exactly the same of the length given by the distance induced by the length structure. So by the Finsler structure. So this is the length induced by the Finsler structure, and this is the length induced by the distance induced by the length induced by the length structure, by the Finsler structure. Okay, you can find this proof in the lecture notes, but it's exactly the same that we did for vector spaces. I will focus more on the reason why the length structure induced by the distance induced by the Finsler structure is equal to the length structure induced by the Finsler structure. Okay, so let's see the first inequality. This is easier. So the distance induced by the Finsler structure, what is this? Between 2 points, gamma s and gamma t of a curve. So So this is by definition, is this the infimum or all curves that joined these 2 points and that are absolutely continuous. So, the length, so it's parameterized still with S and T of a curve. I take the derivative, it's absolutely continuous, and this is the length with respect to the Finsler structure. Okay, so since gamma is a competitor, is absolutely continuous, then this infimum is less than the integral between S and T of the norm of the derivative of gamma. And this, by definition, this is what we were calling the length with respect to the Finsler structure of the curve. Okay, now we have gamma restricted to the interval ST. So, see, for each interval of gamma, we have that the distance between the extreme points is less than the length. So now, by the definition of length, you just divide the interval AB, the domain of gamma, 2 points, take the sum, take the supremum, this is also additive, add, take the sup, you will always have that then for the length with respect to this distance is less of the length with respect to the Finsler structure. Right? So with this one here. Okay, so we got one inequality. The other one. Greater or equal. Okay, so what do we do now? So we have to use now that the norm is continuous. Okay, so let's write more explicitly, like the norm of a vector tangent at x. Let's write it really as a function of 2 variables, right? X and v. So now let's put ourselves in coordinates. So we have x that belongs to some open sets of Rn, where n is the dimension of the manifold, and that we have that v is a vector at x. But since we are now in a vector space, or an open set of a vector space, we can identify the tangent at x with all Rn. Okay. So now the function f, the norm, is a function from u to times Rn valued into, and so this is an open set of R to n valued into R. Whenever you fix u x in u, then you get a norm on Rn, and this function is continuous. This is continuous. Being continuous, what we have is that whenever we fix an error k greater than 1, then, and we fix a point P in U, then there exists a neighborhood, let's call it UP of P, such that if we freeze, right, the norm P, so we look at the constant norm with P fixed, but now we let Q vary, so we look at another Q close by, right? So these two are norms that are comparable, and the ratio of them is as small as we want, as long as Q is in a neighborhood, in the neighborhood of P. So let's put an error. Okay, same up F Q E, and this is for all Q in this neighborhood of P, and for all V tangent vectors in Rn. Okay, so this is an important formula. Let's put a star here. Okay, we're going to use it a couple of times. So now what we have done is the following. We have the curve gamma, and for every point we know that I have a neighborhood where we can freeze, so we can compare the norm at different points to the norm of a given point in here, and the ratio is bounded by k. So now what do? We partition the curve in such a way that on each interval we have the same bound k. So what do? We partition the domain of gamma what was AB, with points A0, which is A, less than A1, dot, 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 up to AN, which is B, such that the image of the curve gamma restricted to the interval AI minus 1 AI is contained in U gamma of AI. This is for I from 1 to N. Okay. Now, what do we have? We have that, so for all I, f of gamma AI as a function of the second variable, this is a norm. This is a constant norm, right? Constant norm. So on an open set of a vector space, so we can think of on our n. So let's call, so let di be its induced distance. Induced distance. Okay, from the example that we saw for norm vector space, what we have the length structure induced by the Finsler structure given by this constant norm is equal to the length structure of the induced distance of the distance di. And well, this is one fact. Now, again, this fact here tells us that if we consider the distance given by the Finsler structure with the varying norm, or the distance of the length with a fixed norm, this you get two quantities that are by Lipschitz equivalent constant k. So what I claim is that also from star we have that the di is less or equal than k times the distance given by the Finsler structure, which therefore says that if you take the length structure of the I, this is less or equal than k times the length of the distance t. Okay, now we are going to use this formula here and this formula here in the next calculation, and we're almost done. So let's calculate the length with respect to the Finsler structure of gamma. So this is by definition, this is the integral from a to b of f at gamma t, gamma dot t in dt. Okay, so let's break this integral into n pieces. So this integral from t n I minus 1 to ti of the same quantity, gamma t, gamma dot ti. So, I didn't do anything, I just split the integral dt. Okay, now on each interval we have that this f is bounded, this is the star, is bounded by k times the constant norm when we put gamma of ti, gamma dot t dt. So you see, I froze this variable, but of course this is still varying, okay? So same domain of integration. Okay, now what do we do? Now remember, this is a constant norm, so we have by the first property, this one here, that the length of the I is the length of the constant Finsler. So what is this? This is the length of with respect to the constant Finsler structure, but we know that this is the same of the length with respect to the distance given by the norm of the curve gamma. So we apply this to gamma restricted to the interval ti minus 1 ti. Okay, now each d each di has a length that is less than k times the length of the Finsler structure. So this is by 2. We have another k, so it becomes k squared. The length of d of the Finsler structure of gamma restricted to the same intervals. And now by additivity of length, now this is the this is the length, same length. So you touch these curves, and then you exactly get k squared length respect to the distance induced by the Finsler structure of gamma. Now this is for all gamma, for all k, and k was arbitrarily less than 1, greater than 1. So you also got this length is less than this length, and we are done. Okay. Now, to conclude, I really want to make a remark about the fact that I was actually only talking about absolutely continuous curves. So I want to remark some facts. So of course, so what we understood that if gamma from AB into M is absolutely continuous, remember this does not really depend on the Finsler structure. It's, in coordinate is the integral of a function. Then then first of all, the Finsler length is finite, right? So you can integrate. Right? And we also proved that the length with respect to the distance induced by the Finsler structure of gamma is equal to the length of the Finsler structure, which is finite, right? So in other words, all absolutely continuous curves have finite length. Now, first, another thing to note is that if gamma is not absolutely continuous, then actually the Finsler length is not even defined. Like we cannot integrate. We don't know how to integrate. Okay. However, if the length with respect to the Finsler norm is finite, with respect to the distance induced by the Finsler structure is finite, then up to reparametrization, gamma is Lipschitz. So for example, we can reparametrize by arc length Lipschitz with respect to the distance d. But this distance in coordinates is by Lipschitz equivalent to any Euclidean distance. So, and therefore, with respect to any Euclidean distance. This was all in coordinates. But therefore, by Rademacher, we have that gamma is absolutely continuous. Okay. To summarize, in Finsler structures given by a continuously varying norm, the curves of finite length are exactly the absolutely continuous curves. And for them, the Finsler length is equal to the length with respect to the induced distance. If you like the video, you can let me know by clicking the like button. This will also suggest the course to other people. If you want to see more videos on subRiemannian geometry, please subscribe to the channel clicking below. Bye.